Hello, colleagues, students, and friends. So on behalf of Nova Links and the Computer Science Department of FCT Nova, welcome to our 9th distinguished lecture, which features Scott Aaronson from the University of Texas at Austin. This distinguished lecture series aims to bring to the department some of the most influential researchers and practitioners in computer science, providing students and researchers with the opportunity to know more about some of the most groundbreaking work in our field and the people who lead it. The series hosts one talk every year. It started back in 2012 with the inaugural lecture given by Turing Award winner Barbara Liskov, who was followed by other outstanding computer scientists such as Thomas Enziger, Jeanette Wing, and also Turing Award winner Leslie Lamport, among many others. These sessions usually take place on campus in our main lecture hall, which is usually packed with hundreds of students and faculty. Even though this time around we could not assemble on campus, we did not want to break this lecture series tradition and decided to host it as a Zoom session nevertheless. Of course, we're all looking forward to meeting in person again and regaining some sense of normalcy. But on the positive side, having it as a Zoom session makes it easier for colleagues from out of town to attend. And I'm happy to see that so many of you colleagues and students were able to join us today. So without further ado, I hope you enjoyed this distinguished lecture, and I'll now yield the floor, or the screen to be more precise, to my colleague Luís Caires, the director of Nova Links, to present this year's speaker. Luís?
Okay, so thanks, João. So hello, everyone. So as João just said, so my name is Luís Caires, and I'm the director of the Nova Laboratory for Computer Science and Informatics at FCT Nova. So quantum computing really promises to revolutionize information technology of the future by leveraging on this deep quantum physics phenomena to increase the speed of computation to levels imagined never before. Quantum computing is actually strategic research all over the world, leading to big bucks initiatives in the European Union, the US, China, and being also under the spotlight in many other countries, including Portugal. Quantum computing is also being obsessively explored by tech giants like IBM, Google, and Microsoft. But really, what is quantum computing? What are its promises and challenges? What has been already achieved? Well, to tell us all about it today, we are really honored to have with us Scott Aaronson, computer scientist, leading expert in models of computation and quantum computing, inventor of bosonic sampling, a new way of implementing quantum computers using light. Scott Aaronson is professor of computer science at UT Austin, where he heads the Quantum Information Center. He received a bachelor from Cornell and a PhD from the University of California at Berkeley. Before joining UT Austin, he was for almost a decade a professor at the MIT. He received the National Science Foundation's Alan T. Waterman Award, the United States PK's Award, the Vandermeer Bush Fellowship, and the Tomasonic Isesi Prize in Physics. He is also since recently, a fellow of the Association for Computing Machinery, since last year, essentially. Scott is also frequently engaged with non-academic media and channels such as Closer to Truth, Science News, New Scientist, New York Times, Forbes magazine, about quantum and many other science topics. In fact, I would like to conclude my short introduction of Scott by citing Scientific American writer John Organ preamble to a 2016 interview that summarizes pretty much what Scott is really like, a 21st century polymath. So he says, Scott Aaronson answers every ridiculously big question I throw at him. Quantum computing with riffs on simulated universes, the singularity, unified theories, the P versus NP problem, the mind-body problem, what is free will, why there's something rather than nothing, and many more. So we are all looking forward to this talk today. After the talk, there will be a short Q&A session, so please type your questions in the Zoom chat box so that we may know about them later. Okay, that's it. So thank you very much, Scott, really, for sharing your insights with us today, and the floor is yours. Scott.
All right. Well, thank you so much for that incredibly kind introduction. I won't be able to live up to that, nor will I explain what free will or the meaning of life are today. But it's a pleasure to be here. I visited Lisbon once in 2006. I had a wonderful visit, and I wish that this could also be an in-person one. But we do what we can. So I want to tell you today about quantum computational supremacy and its applications. You know, I am not an engineer. You know, I am almost as far as you can get on the theoretical side of quantum computing. But one of the things that's so exciting in this field is that, you know, within the last 5 years or so, the experimentalists and the theorists are actually talking to each other. You know, and you know, and not just for fun, but we really need to. There are finally devices that can do some of the things that you know we were thinking about when, let's say, I first entered this field, which was about 20 years ago. I'm pretty sure that this image here is not what a quantum computer looks like. At least it's not what I saw on any of the lab tours I did. This is what you see if you do a Google image search for a quantum computer. Okay, so because it's a broad audience, I should start with a little bit about what is a quantum computer. And in order to answer that question, we first have to say, what is quantum mechanics? So quantum mechanics has been the basic operating system for physics for almost 100 years. You know, people often have the impression that it's complicated, it's confusing. Well, maybe confusing, but you know, because I'm not a physicist, I can sort of let you in on a secret, which is that quantum mechanics is actually a lot simpler than the physicists say it is, at least once you take the physics out of it. So the way that we tend to think about quantum mechanics in quantum computing and information is as a certain generalization of the rules of probability themselves. Okay, you know, it's a generalization that the entire world happens to be based on. Although we most notice it if we're doing experiments at the scale of you know, electrons and photons, atoms and molecules. Okay, so you know, and the basic starting point is what are probabilities, right? A probability is a real number from 0 to 1, of course, that, you know, quantifies your degree of belief that something is going to happen. You know, you could talk about a you know, a 30% chance that there would be rain tomorrow, you know, or a probability that there would be an insurrection at the American Capitol. You know, that would clearly be, you know, 0.1% or something. That's, you know, clearly something that wouldn't happen. But you know, in any case, we would never talk about a negative 30% chance of something happening, right? That would just be nonsense. Far less would we talk about an I percent, you know, a square root of -1% chance. Okay, but what quantum mechanics tells us is actually that to each possible way that the universe could evolve, or that, you know, you could see a system like an electron, say, when you measure it, you have to assign a number called an amplitude. Okay, and amplitudes can be positive or negative. In fact, they can even be complex numbers. Okay, and now they are related to the probability that you will see something when you look, but they're not probabilities. Okay, they work differently. What the rule says is that if I want to know the probability that something will happen, like let's say that I will see an electron at a certain spot on a screen, the probability is the squared absolute value of the amplitude. Okay, and now crucially, the amplitude is the sum of an amplitude from every possible way that the thing could have happened. Okay, so as an example, you know, and this is the famous double slit experiment, right? That Richard Feynman used to say that everything in quantum mechanics can be explained via this one experiment, right? I shoot an electron at a screen with 2 small slits in it. I look at where it ends up on a second screen, and I find that there are certain places where it never appears, okay, or is very unlikely to. And the explanation of this, according to quantum mechanics, is that, well, it had an amplitude to get to those spots by going through the top slit. and it also had an amplitude to get to those spots by going through the bottom slit. Okay, but one of the amplitudes is positive, let's say, and the other one is negative. And as a result, they interfere destructively. They cancel each other out, with the result being that the total amplitude is 0, and then the event never happens at all. Okay, now the striking demonstration that this is what's going on is if you close one of the slits. Okay, then you find that the electron can appear in these places where previously it couldn't. Okay, why? Because now the amplitude, we only have a positive amplitude, or we only have a negative amplitude, right? We've closed off the other one. Okay, so to say that again, by decreasing the number of ways that a particle can get to a place, we can increase the chance that it gets there. Okay, so that is the result of interference of amplitudes. And anytime you will ever read anything about the strangeness of the quantum world, either it's false or else, it is yet another implication of this change to the rules of probability. Okay, the replacement of probabilities by these complex numbers, these amplitudes. All right, so a little bit more carefully, we can say, if we've got any physical system and it can be in two distinguishable states, which the physicists like to label with these angle brackets. So let's call them ket 0 and ket 1. And this could be an electron that can be either in its lowest energy state or the next higher energy state. It could be a photon that could have two possible positions. Okay, just like with classical bits, right? There are many different physical substrates, and the underlying logic will be the same for all of them. Okay, and what quantum mechanics says is that our object can then be not just in the state 0 or the state 1, but in a complex linear combination of the two states. Something that we write alpha 0 plus beta 1, and what we call a superposition of 0 and 1. Okay, here alpha and beta are amplitudes. Okay, they satisfy a normalization rule. The sum of their squared absolute values is 1. And a superposition could be over any number of possibilities, but if it's only over two possibilities, say 0 and 1, we call it a quantum bit or a qubit. Okay, a qubit is the basic building block of a quantum computer. Okay, just like a bit is the building block of a classical computer. Okay, now if you look at a qubit and you sort of ask it whether it's 0 or 1, then you force it to make up its mind about what it wants to be. Okay, and it will snap to one choice or the other. And famously, it does this probabilistically. Okay, so if you observe to see if the qubit is 0 or 1, it will tell you that it's 0 with probability absolute value of alpha squared, and that it's 1 with probability absolute value of beta squared. And whichever choice it makes, it will then snap to that choice. Okay, so the other possibility is now lost forever. Okay, but now if the qubit is isolated, if it's kept separate from everything else in the universe, then the amplitudes will evolve by rules that are different from the rules of classical probability. Okay, and particularly the amplitudes will evolve by a linear equation. Okay, this is the Schrodinger equation, the central equation of quantum mechanics. Basically, just says that the amplitudes change in time by the vector of amplitudes gets multiplied by a matrix. It gets linearly transformed. Okay. Now, crucially, if I have 100 qubits, let's say, the rules of quantum mechanics are unequivocal that I don't just need separate amplitudes for each qubit. Okay, rather, I now need 2 to the 100 power amplitudes. Okay, I need one amplitude for every possible 100-bit string, every possible configuration of all 100 of the bits. Okay, and in general, if my qubits could interact with each other, they can form what's called an entangled state. Entangled simply means that by measuring one qubit, I can learn something about the other qubits. Okay, so it's the quantum version of being correlated. Okay, and if I have 1,000 qubits, which I could store in just, let's say, 1,000 particles, which is not a lot of particles that could fit on the head of a pin, but still, to describe their state, I would in general need 2 to the 1,000 power amplitudes. Okay, that happens to be more than the number of particles in the whole observable universe, which is only about 10 to the 85 power. Okay, and so if you like, just to keep track of the states of very small systems, molecules, materials, and so on, it's as if nature has to maintain this enormous amount of state off to the side somewhere where we can't see it. It has to maintain some scratch paper with 2 to the 1,000 parameters in it, okay, that we never directly see, but we know that it's there because it's what we use to calculate the probabilities of the outcomes that we do see. Okay, so now this exponentiality was known since the very beginning of quantum mechanics. It's in Schrodinger's paper in 1926. And chemists and physicists knew about it for decades. They knew it mostly as a practical problem. If you're trying to simulate quantum mechanics with a conventional computer, then in general, the number of parameters that you need to keep track of doubles or worse with every particle that you add. Okay, and so for generations, the chemists and physicists sought to develop clever hacks to get around that problem in various cases. They often won Nobel Prizes for inventing good hacks, like the so-called density functional theory. And they used very powerful computers to try to simulate quantum mechanics. Some of the biggest supercomputers on Earth are used for that. But there is a limit to how large of a quantum system they can simulate because of this exponentiality. Okay, it was only in the early 80s that a few physicists, most famously Richard Feynman and David Deutsch, had the remarkable idea that if nature is giving us this computational lemon, why don't we make lemonade out of it? Or in other words, why don't we build computers that themselves would be made of qubits and that themselves could form these huge entangled states and exploit exponentially large superpositions and interference of amplitudes. Okay, this is precisely what we know, what we and they call a quantum computer. Okay, now of course they almost immediately face the question, well, supposing that we built this quantum computer, what would it be good for? Okay, and at the time they really only had one answer to that question, which is it would be good for simulating quantum mechanics itself. If and when quantum computing becomes truly practical, that is still the most important real-world application that we know of. It has an enormous range of possible uses to designing new materials, new solar cells, high-temperature superconductors, new chemical processes. Okay, what really made most of the world excited about the field was another development that came a decade later in the 1990s. And this was the discovery that if you build a quantum computer, you can sometimes get it to solve even a purely classical problem faster than a classical computer could solve the same problem. Okay, and now I have to warn you that most of the popular articles that have been written about quantum computing over the last 25 years, describe it in a very misleading way. Okay, what they say is something like, well, a quantum computer could just try every possible answer in parallel. It could try, sometimes they'll say, it could try each one in a different parallel universe. And then somehow it just magically picks the best one. Okay, well, that would of course be amazing if true. That would be revolutionary. But unfortunately, it is not that simple. Okay, a quantum computer is not just like a classical computer, except exponentially parallel. In fact, I used to have this as just a tagline of my blog because the confusion is so frequent. Okay, so here's what's going on. Okay, it's true that with a quantum computer, you can create a superposition over all the possible answers to your computational problem, even if there are exponentially many possible answers. Even if, let's say, your problem is NP complete, like the traveling salesman problem or something like that. The trouble is, for a computer to be useful, at some point you have to look at it. You have to measure its state. Okay, and if you just measure it in equal superposition, not having done anything else, the rules of quantum mechanics tell you that all you'll see will be a completely random answer. Okay, and if you just wanted a random answer, well, you could have picked one yourself with a lot less trouble. Okay, so then what is the point of building a quantum computer? Well, the entire purpose is to exploit the way that these amplitudes, being complex numbers, work differently from conventional probabilities. Okay, it is to exploit interference of the amplitudes. Okay, and the basic idea with every algorithm for a quantum computer is that you are trying to choreograph a pattern of interference so that for each wrong answer, each answer that you don't want to see, some of the paths leading to it have positive amplitudes and others have negative amplitudes. So they interfere destructively and cancel each other out. Okay, whereas the paths leading to the right answer should constructively interfere. That is, they should have amplitudes all or mostly of the same sign. Okay, so they all add up. Okay, if you can arrange that, then when you measure, you will see the right answer with a high probability. Okay, and of course, if you don't see it, you can always just repeat the computation several times until you do. Okay, but the name of the game, quantum computer science, is always to design this pattern of interference that boosts the amplitude on the correct answer. Okay, and the tricky part is you have to do that even though you yourself don't know in advance which answer is the right one. If you knew that, then there would be no point. And you have to do all of this much faster than even the fastest classical algorithm could do the same thing. Right? This is the hard part about quantum computing, that it's not enough to build a quantum computer and have it work. In order to be interesting, you have to beat the best that anyone could do using a classical computer. Okay, so that's the theory. Now, how do you actually build quantum computers? There are a whole bunch of approaches that are being pursued in parallel right now. As I said, the basic logic of qubits applies to, in principle, everything in the universe. Although you mostly notice it when things are very small. So people have tried building qubits as the spin states of atomic nuclei, as ions that are trapped in a magnetic field, and which are then manipulated using lasers. This is an approach being pursued by IonQ, a startup out of University of Maryland, also by the company Honeywell. You can use cold atoms, like Misha Lukin at Harvard is doing. You can use photonics, so you can use light as your qubits. Company PsiQuantum in Palo Alto is doing this, as is a group in China, as I'll tell you about later. And with all of these approaches, people today can build systems with a few dozen qubits, or even a few hundred qubits. Although then you sort of lose the ability you want to control them, right? But when I entered this field 20 years ago, people were still trying to get 1, 2, and 3 qubits to work, basically. And today we're talking about systems with 50 to 70 qubits that are integrated, that are programmable. Okay. The approach that is maybe the furthest along today is called superconducting qubits. This is the one being pursued by Google and also by IBM, also by various startup companies and academic groups. This is where you take a chip, it looks like a normal computer chip. You put coils onto it that can store currents in two different energy states that you could call 0 or 1. But then you cool the chip to nearly absolute zero, okay, about 10 millikelvin, so 1/100th of a degree above absolute zero. And that causes the currents to superconduct, meaning that they can now flow in a superposition of the 0 state and the 1 state. Okay, now crucially, we have control devices called Josephson junctions, where we can control what each qubit is doing, and we can also get any pair of neighboring qubits on the chip to interact with each other in a prescribed way. Okay, and we have some classical control electronics, controlled by our classical computer that is outside of the refrigerator. The refrigerator is this thing down here that looks like an upside down wedding cake. And we are sending signals into the refrigerator, into the chip, to control what each qubit should do when. Okay, so the device is fully programmable. That's why we call it a computer in the first place. Okay, now Google and others are working to scale this approach up to hundreds of qubits. We don't know. It looks very hard to get beyond that. And then there are even more exotic approaches, like what's called topological quantum computing, or non-abelian anyons, which is being pursued by Microsoft. This approach, on paper, it looks like maybe the best way to scale quantum computing to however many qubits you want. But so far, they haven't managed to build even 1 qubit this way. Okay, in order to make it work, you have to create a new state of matter, which has never been seen in nature. Okay, that's what they're trying to do. Okay, so let's step back and ask, why is building a useful quantum computer such a hard engineering problem, right? I mean, it's great that we're now talking about 50 or 60 qubits, but why not 50 million qubits, right? What's the holdup? Well, the central engineering difficulty was understood from the very beginning of the field, and it's called decoherence, or loss of quantum coherence. Basically means unwanted interaction between the quantum computer and its external environment. Okay, this has the effect of prematurely measuring the qubits and collapsing their state, right? I told you before that if you look at a qubit, right, you force it to decide whether to be 0 or 1 randomly, and it collapses to one or the other, okay? But crucially, it doesn't have to be you who's looking, right? Any stray radiation, or any defect in the material, or even the air in the room, or anything like that, anything that interacts with your qubit and that carries away any information about whether that qubit was a 0 or a 1 will have exactly the same effect on the qubit as if someone had measured it. Okay, that is, it will look exactly as if the qubit had been measured. In a sense, it has been measured. It's not by a person, but by a stray particle. Okay, and that destroys the quantum state. Okay, that makes it behave classically rather than quantumly. Okay, this is why we only notice quantum effects at the microscopic scale. Because on the scale of everyday life, this decoherence is everywhere. Okay, so what this means in practice is that if you want to build a useful quantum computer, you have to keep the qubits incredibly well isolated from everything else in the universe so that they maintain their quantum state. But at the same time, the qubits have to interact with each other, okay, and do so in a precisely prescribed way. Okay, so it's those twin requirements that make this so hard that there have even been very smart people from the 1990s onward who said, this is impossible. Okay, this will never be done. This will always just remain on paper. Okay, now there was a fundamental discovery in the mid-1990s that convinced most physicists and computer scientists that, in principle, a quantum computer should work. That the difficulties are merely, staggering difficulties of engineering, okay, and not any difficulty of principle. And this was the discovery of quantum error correction and quantum fault tolerance. And basically what that said is that you don't have to get decoherence down to zero. Okay, it is enough to make the decoherence very, very small. Okay, and as long as the rate of decoherence on each qubit is low enough, you can encode the qubits that you care about using very, very clever error correcting codes across the states of many physical qubits in such a way that even if some of the physical qubits are leaking out, their state into the environment, you can detect that that's happening and you can correct for it. Okay, you can recover the qubits that you care about from the collective degrees of freedom. Okay, unfortunately, to actually get this fault tolerance to work, it's sort of like a bootstrapping problem, right? Because as you try to correct error, you're also introducing more error, okay? And you might worry that you're just going to make things worse and worse. Okay, well, it turns out, the theorem people proved in the 90s says that once you get the physical decoherence rate down to a certain threshold, then there is a crossover that happens where each round of error correction that you do starts making things better rather than worse. Okay, so before you get to that crossover point, everything that you build is, you could say, we're sort of like, we're in the Charles Babbage era of quantum computing, or maybe the vacuum tube era, okay? But we don't yet have the transistor, right? We can't yet scale reliably, okay? So we might be able to do something useful, but in order to get true scalability, you need this, you need to get past this threshold where error correction becomes a net win. And that's been the central engineering goal of the field for 25 years. We are orders of magnitude closer than people were, 25 years ago, still not quite there. People are racing to get there, over the next decade or so. Okay, but in the meantime, we could hope, that even before we have error-corrected quantum computers, can't we at least do an experiment that would prove the point that a quantum computer can do something faster than a classical computer could simulate it? Okay, so or at least that we know how to simulate it with any existing classical computer. Okay, this is the idea of what's been called quantum supremacy. Okay, the term was coined in 2012 by the physicist John Preskill. Not everyone likes it, but the term seems to have stuck. And what he meant was simply, using a quantum computer, which might be a noisy one with only 50 or 100 qubits, to do some computation that is classically hard. Okay. Notice I did not say a useful computation. It doesn't have to be good for anything. It could be some completely artificial benchmark, but we want to demonstrate, in practice that we can beat a classical computer at something. Okay, I like to joke that for me, this is the #1 application of a quantum computer. Okay, more than simulating quantum mechanics, more than optimization problems or breaking cryptographic codes or any of it. I just want to disprove all of the people who say that a quantum computer could never work. Okay, so how could we achieve quantum supremacy? Well, the great theoretical discoveries of the 1990s would seem to give us, obvious ways to do that. So Shor's algorithm, discovered 27 years ago, showed how if you build a scalable quantum computer, then you could use it to efficiently factor large integers. Right? And this is probably the most famous quantum algorithm that there is. Okay, this is really what put this whole field on the map. Okay, and why do we care? Well, because of course, almost all of the encryption that we use to protect the internet, the public key encryption, is based on the belief that factoring and a few closely related problems are hard. Okay, what Shor showed that if you build a quantum computer, that's no longer true. Okay, you can break RSA, break Diffie-Hellman, break elliptic curve encryption. Okay, so of course, this made many people excited about quantum computing who hadn't been before. The trouble is, Shor's algorithm seems very, very demanding to implement if you actually want to get a speed up with it. I mean, people have done tiny demonstrations like factoring 21 into 3 times 7, with a quantum computer. But if you actually want to break RSA, then it seems like you will really need a fault-tolerant, error-corrected quantum computer, which would mean thousands of logical qubits, which then, because of the error correction, would translate into millions of physical qubits. Okay, so we're just not there in the near future. Okay, yeah. So this brings us to a completely different idea for how you could demonstrate quantum supremacy, and this is the path that was actually followed by Google, and by the group at USTC in China over the last few years. And this idea, this different approach, came out of theoretical work that some of us did about a decade ago. So in particular, my former student, Alex Arkhipov, and I introduced a proposal called boson sampling, which was just a very rudimentary type of quantum computer where you generate photons, you send them through a network of beam splitters, and then you measure where they ended up. And that's all that you can do in this model. And what is it useful for? Well, we had and still have no idea. Okay, but we were able to give evidence that a boson sampling experiment would sample from a probability distribution that a classical computer would have a hard time sampling from. At least based on our current beliefs in computational complexity. Okay, so so to be clear, we are switching attention from problems like factoring that have a single right answer that you're looking for to sampling tasks. So problems where there are many, many different valid answers. The task for the computer, the challenge, is to sample an answer randomly, okay, but not completely randomly, but according to a prescribed distribution, where some answers should be likelier than other ones. Okay, and we are, now we get to sort of design a distribution that is easy for a quantum computer to sample from, but hard for a classical computer to sample from. And it turns out that once you switch the goal in that way, you get 2 big benefits. First of all, the theoretical evidence that your quantum system is hard to simulate with a classical computer actually becomes stronger. Okay, we can easily design things that we've got no idea how to simulate classically in less than exponential time, and we can even justify that belief based on some known complexity theory. Okay, but secondly, we get proposals that are somehow much closer to experimental realization. Okay, they're much closer to what the experimentalists can actually do today with the noisy, 50 qubit devices or 50 photon devices that they can build now. Okay, and so so we came at it from purely the theoretical direction, but then the experimentalists sort of taught us that we should focus on we should sort of adapt the theory to what they can actually do in the near future, and that's been one of the more exciting things I've ever been involved with. Okay, so this brings us to Google's quantum supremacy experiment, which it announced to great fanfare a little more than a year ago. So just before COVID shut down the world, basically. And so, as I said, Google is building devices with superconducting qubits. And what they decided in 2015, they hired John Martinez, who was, maybe the top superconducting experimentalist in the world. And he said, we want to do something like boson sampling, okay? But, we're not going to use photons like Aaronson and Arkhipov had said. We want something that is more adapted to our system. And so they built this 53 qubit chip, which they called Sycamore. If you're wondering why 53 qubits, it's a weird number, well, they manufactured 54 in a rectangular array, and one of them didn't work, which is, apparently common. So now this 53 qubit chip, they apply actually just a random sequence of operations to it, okay, to the qubits. And this gives them some state on some entangled state on all 53 qubits. Okay, so to describe that state, you need 2 to the 53 amplitudes. Okay, that's about 9 quadrillion complex numbers. Okay, and now we want to, demonstrate the reality that, sort of that is what's there, and that is what you would need if you wanted to simulate this thing with a classical computer. So what we do is we sample. We repeatedly measure the 53 qubits, and we see whether each one is a 0 or a 1, right? So each time we sample, we get a 53-bit classical string, right? And so we get a bunch of independent samples from a distribution over 53-bit strings, okay? And, crucially, the chip is very fast. So taking each sample only takes about 40 microseconds, which means that in about 3 minutes, we can take millions of samples. Okay, and this is important because there's a lot of noise in the chip. In fact, there's only about 0.2% signal and 99.8% noise. Okay, but when you have millions of samples, you can do statistics to extract the signal even with that level of noise. Okay. And now, as I said, each time you do the measurement, you will see a different outcome, right? You'll probably never see the same outcome twice in the whole lifetime of the experiment, okay? But the outcomes are not uniformly random, okay? Some are likelier than others. And why is that? Well, basically, it's because of interference, okay? It's because each final amplitude, okay, the amplitude of each possible output string is a sum of, many contributions. And, some of those contributions are positive, some are negative, they can be all different complex numbers. And so they largely cancel each other out, okay? But just by chance, the cancellation will be more perfect for some of the outputs than it will be for others, okay? So some of the outputs will end up with somewhat larger amplitudes than other ones. So some outputs might end up with a probability of 1 in 20 quadrillion, and others might end up with a probability of 1 in 2 quadrillion, something like that. There were little fluctuations because of the quantum interference, okay? And so now, and if you know the circuit, the sequence of operations that was applied, then you can actually calculate those fluctuations, given your classical computer, and using brute force, using 2 to the 53 time on a gigantic supercomputer. Okay, and so now that means that you can do statistics on the outputs that you see from the quantum computer. You can say, are these outputs consistent with having been sampled, from this distribution? Like, are the ones that were predicted to have larger probabilities actually more likely to show up? Okay, so and that's exactly what you do. John Martinez likes to use the analogy of speckle. If we sent some laser light through, ground glass, then just because of quantum interference, photons are more likely to emerge in some places than in others, right? So we get a pattern with some like light spots, some red spots where the photon often shows up, and then black spots where there's more destructive interference, more cancellation, and where it's less likely to show up. Okay, So what we did, my students and I, once we knew that Google was doing this, then we decided to sort of port the theory of boson sampling to the type of experiment that Google was doing, and sort of try to understand, well, is it really hard to simulate it with a classical computer? How do we know that? Based on what kind of theoretical assumptions? And also, what should Google do to verify the result? Okay, so the thing that they ended up doing to verify the results is almost one of the simplest tests that you could apply. They called it the linear cross entropy benchmark, or linear XEB. Okay, and basically all you do is you collect all of the samples that the quantum computer generates. Let's say that the samples are called S1, S2, up to SK. Where, each SI is a string of 53 bits, and let's say K is a few million. Okay, now using your classical computer and using lots of brute force, you calculate for each SI what was the predicted probability that an ideal quantum computer would have generated it. Okay, that's this squared absolute value here. And then we simply take those probabilities and we sum them all up. Okay, and we consider the quantum computer to have succeeded at its task if and only if this sum exceeds a certain threshold. Okay, now what is that threshold? Well, if I just pick samples completely at random, so, not even using a quantum computer, then I would expect each probability to be 2 to the minus n on average, where n is the number of qubits. And so if I add up k of them, I'm going to get about k divided by 2 to the n, right? If, on the other hand, I have a perfect quantum computer, then you can do a calculation that says that this sum, on average, will be about 2k over 2 to the n. Okay, so exactly twice the sort of naive classical value. Okay, so it's now all a game of how large can you get this sum to be, right? Or this is sort of your signature for quantum supremacy. Okay, and now, long story short, in its experiment, Google reported a value of this constant b here, which was about 1.002. Okay, so again, 1 would be trivial. That's just a classical computer generating the samples randomly. 2 would be an ideal quantum computer with no noise. Okay, so as you can see, we are very, very far from ideal, right? But we're just barely detectably above what the classical computer would have given. Okay, but this is good enough. Okay, because we can, we have enough data to see that this 1.002, is really larger than 1, to, I think 10 or 20 sigmas. Okay, so we have violated the inequality, right? We have, and we think that the theoretitic evidence is that a classical computer would have a very hard time even to spoof this test, okay, even to generate any samples S sub I that would have any b value that is bounded above 1. Okay, so some of you might have seen that just a few weeks after Google's paper came out, which it actually leaked by accident, IBM, which is Google's main competitor in superconducting qubits, published a rebuttal. Okay, their first rebuttal was that we reject the entire concept of quantum supremacy. They said we just care about solving practical problems for customers. I personally thought that was kind of weak. Okay, but then a few weeks later, IBM came out with a more robust response, which is they said, well, we think that we can simulate Google's chip using a classical computer, a lot faster than Google thought. So Google, was estimating that simulating their chip classically with the algorithms that they knew might take 10,000 years. Okay, but IBM said, well, look, if you use the literally biggest supercomputer on the planet, which is called Summit at Oak Ridge National Lab, which fills the area of 2 basketball courts, and it has 250 petabytes of hard disk space. Okay, that is enough that you could literally just take this entire quantum state, all 9 quadrillion amplitudes, and write them to hard disk. Okay, and in that way, you could just simulate the quantum computation by brute force. And they didn't actually do it because, you know, it would cost many millions of dollars to get the time on this supercomputer. But, you know, they estimated that if they did it, you know, that they could simulate a sycamore in only a few days. Okay, so, you know, now, you know, to me, you know, it was embarrassing on Google's part that they missed this. They just weren't thinking about writing everything to hard disk. Okay, but, you know, we could also say if this is the best response, then it's almost like a backhanded compliment, right? It's almost proving the point. It's saying, you know, with the literally biggest supercomputer on Earth, you know, you can not quite match the performance of the quantum computer, right? And if you're even within a factor of a few thousand, well, then, you know, it is predictable that in a year or two, you know, even the biggest classical computer won't be able to keep up at all. Okay, now, you know, there is an irony here, which is that once the classical computers can no longer keep up at all, then how do we even verify the results, right? Even in its experiment, Google resorted to some indirect forms of verification for the hardest experiments that it did. Okay, but there is this cat and mouse game, right? That to be really confident about the results, we ironically need a classical computer, you know, doing this 2 to the n brute force thing. And, you know, and that is a drawback of these experiments. We would love to figure out a way around that. All right, so now until very recently, you know, it was said that, you know, these quantum supremacy experiments based on sampling, you know, they might be, you know, impressive, or, you know, they might you know, prove the point that, you know, humanity is capable of, you know, beating silicon chips, you know, via quantum computers for something, but they are clearly useless for anything besides proving the point, right? It just, you know, just like you wouldn't take any passengers on the Wright brothers airplane, right? You know, who cares about these sampling problems where, you know, all you're doing is you're sampling from these, you know, these random strings that are not uniformly random, but it takes heroic effort to distinguish them from something that's uniformly random. Okay, now a couple of years ago, I realized that, you know, these experiments actually might have an application, okay? And the application is, well, maybe not surprisingly, generating random bits. Okay, now, just to be clear, you know, if you just want random bits and you trust your device, you trust your hardware, then it's, you know, this is very easy to do, right? There are lots of random number generators that you can even buy online right now. You know, some of them exploiting quantum mechanical phenomena to generate the random numbers. Okay, now the trouble is, what if you want to download random numbers over the internet? Okay, and what if, you know, you really need to trust that they are random? Let's say that we want to do a proof of stake cryptocurrency, like the next generation Ethereum, you know, that would where we need to constantly run a lottery to decide who gets to add the next block to the blockchain. So then, you know, we need a website, let's say, where everyone can download some random bits and everyone trusts that they were generated randomly, right? Well, how do you do that, right? How do you know that the NSA or someone has not, you know, backdoored the random number generator and replaced it with something pseudo-random, replaced it by something that they can predict? Okay, well, these quantum supremacy experiments, in principle, could offer a solution to that problem. Okay, and the reason is that, you know, if you can prove that you are passing this linear cross entropy benchmark that Google was doing, so if you can prove that, you know, you are you know, sampling from this distribution, I mean, you know, you are first of all, you know, persuading people that you really have a quantum computer, right? That was the original purpose of these experiments. But as a byproduct of that, you are also demonstrating to a skeptic that, presumably, you must have been generating these samples randomly, right? Because, you must have been using a true quantum computer to generate them. And, we don't think that you could have done it using a classical computer with a pseudo-random generator, right? So, one can make these statements much more formal. One can say under some stated complexity assumption, any samples that are, generated quickly and that pass this test of linear cross entropy must have at least, a certain amount of genuine entropy in them, which can then be purified, extracted, and used for cryptographic applications. So, Google has actually been working to try to demonstrate this application. I don't know how useful it will be, but if it does end up being useful, it might be the first realizable application of quantum computing, because you could do it with the kind of quantum computers that they've already built. Okay, now the latest news in this area is from just a couple of months ago. Okay, and this was from a group in China, which was led by Chaoyang Liu and Jianwei Pan at USTC in Hefei. And they, even after Google achieved quantum supremacy using superconducting qubits, the Chinese group continued pushing forward with boson sampling, which was Mayan Arkhipov's original proposal from 2011. And they built an optical setup where they generate about 50 photons on average. They send them through a network of interferometers. They measure where they end up. And this samples from a distribution that, for all we know today, seems hard to simulate with a classical computer. Okay, in fact, possibly even harder than Google's experiment was, because for this one, you have an enormously larger number of possible output states. And so you're not open to the kind of attack that IBM proposed against Google's experiment, right? You have way too many possible outputs to store all the amplitudes on a hard drive. There's like 10 to the 30th outputs instead of merely 10 to the 16th. Okay. The trouble is, it is a bit harder than it was with Google's experiment to figure out if there might be some clever classical way to simulate this experiment. And this has to do with some technical features of boson sampling and with the fact that there's a lot of loss in their experiment. Okay, a lot of the photons are getting lost on the way through. I think about 30% of them make it, 30% of the photons actually make it through to be detected. And we're not really sure when that many photons get lost if there will be a clever classical way to spoof the results. A lot of experts are working on that question right now, and we hope to be able to say more about it before long. But I think that quantum supremacy is important enough that I am thrilled that people are trying to replicate it with different forms of hardware, with different experiments. I think this is, it really does, take us to a new era in this field. The post-quantum supremacy era. And it means that now we can really concentrate our full attention on getting to error correction, getting to full scalability. Okay, but having said that, I think that there is more to do, even in just nailing down the case for quantum supremacy. I would like these experiments to be done with less error. I would like them to be replicated in more hardware platforms. And finally, on the theoretical side, I would love, as I mentioned before, I would love to figure out a fast classical way to verify the results of these experiments so that we wouldn't have to rely on these brute force classical computations to verify the results. And then finally, I would like to know if they're good for anything, besides just generating certified random numbers. All right, so with that, I've used up my time. So thank you for listening, and I'm happy to take questions. All right, well, I see a whole bunch of questions in the chat window.
Okay, so thank you very much, Scott. So maybe I could try to group a little bit the questions that have been popping up. And,
okay, sure.
well, a first issue is more related about possible applications of quantum computing. For instance, Samuel says, can we expect to have a quantum computer system breaking our everyday CQ systems? Along the same lines, Rui asks, do you think quantum computer systems will be more suitable for neural networks where you have to explore a very large embedding space instead of classic algorithms such as sorting, querying a database, and so on? And Jose Alegria also asks, what significant problems, such as grand challenges, are structurally more amenable to quantum algorithms, and which are not?
All right. Well, those are three different questions. So the first one, you know, I mean, as I said in the talk, eventually quantum computers will be able to break the public key encryption that we currently use to protect the internet. Okay, we are not close to a quantum computer that's good enough for that. You know, it would astonish me if it were done in the next decade. But, you know, if it were done in 20 years or in 30 years, I mean, you know, I don't know. That's anyone's guess. And, you know, people who have information that they need to stay secret for 20 years, you know, should probably already worry about this, right? And, you know, the good news is that we already know the solution to that, right? So we already have public key crypto systems that seem secure even against quantum computers. The most famous example being lattice-based crypto systems. Okay, and there is already a push to migrate to those quantum-resistant methods of encryption. You know, NIST in the U.S. is having a competition to standardize post-quantum cryptography. You know, they're not widely used in practice yet, but they could be these other systems. Okay, and I should say a private key encryption is much less affected by quantum computers. There you roughly just have to double the key length to get the same level of security that you had before. Okay, now in terms of the applications of quantum computers, since I didn't get to this in my talk, let me just say, you know, the way I think about it is that there are three main classes of applications that we know about, you know, and possibly others, you know, still to be discovered, right? The first is problems that themselves involve quantum mechanics, okay, like, you know, simulating materials and chemicals, right? You know, this I did mention. This is maybe, you know, the biggest, the economically most important application area that we know, in my opinion. Okay, and it's also our best shot of getting practical quantum advantages in the relatively near future, let's say in the next decade. Okay. Now the second is the code breaking, okay, that we talked about, right? That's, you know, not obviously a positive application for humanity. You know, it's good for whatever intelligence agency gets it first, you know, as long as no one else knows that they have it, right? You know, as soon as people know that you have it, then they just use a different encryption method. Okay. And then the third class of applications is, you know, let's say things like optimization, combinatorial search problems, you know, NP-complete problems, machine learning. But now it's crucial to understand that for all of these problems, the quantum speed up that we expect is more modest than it is for those other application areas. Okay, so there is a quantum algorithm called Grover's algorithm that can basically take any type of combinatorial search problem that involves searching a list of n possible solutions, and it can solve such problems in about the square root of n steps. Okay, so it gets a square root or quadratic improvement compared to a classical brute force method, right? And so that has an enormous range of applications in machine learning, in, you know, optimization, in logistics, you know, in combinatorial search. But it is not an exponential speed up, right? It is only a polynomial speed up, only a quadratic one. And this seems to be inherent You know, we can't prove it. You know, we can't even solve the P versus NP problem, right? But, you know, we expect that for NP complete, you know, types of problems, and for the hardest optimization and machine learning problems, quantum computers are not going to give us an exponential speed up, but only this quadratic speed up, okay, which is significant, you know, but it's not the complete game changer that an exponential speed up would be. Okay, now over the last 20 years, there have been constant claims, you know, to try, you know, that one could do better than this, and attempts to do better than that. There has been an enormous amount of hype in the area of quantum machine learning, including about, you know, quantum neural networks. Okay, the difficult part with all of these proposals is what advantage are you actually getting over a classical computer, right? And anytime someone talks to you about quantum neural networks, that is the question that you should ask them, okay? They may try to talk around it, avoid directly addressing it, just keep asking that question, right? What is the purpose of adding quantum to this neural network? What will it do faster that way, right? You know, astonishingly often, they will have no idea, right? It's just, well, the word quantum sounded good, and neural net also sounded good. So we just put them together and we wrote a paper about it, okay? You know, for me, that's not good enough, right? I want to see what speed up can we expect compared to, you know, classical deep networks, right? And, you know, and we don't really know for, you know, using, like, there are some aspects of, you know, training of a neural net where Grover's algorithm might be able to give you some advantage. For gradient descent, you know, as in back propagation, there might be some quantum advantage there. So, you know, so there are some modest quantum speedups that you can get there, but we don't really know. We don't yet know if there is a sort of machine learning problem of practical importance where quantum computing will give you an exponential speedup. And, you know, I view that as one of the great theoretical open problems in quantum algorithms.
Mm-hmm. Okay,
Yeah.
thanks, Scott. Just
Sure.
well, another bunch of questions. So this one is related about the challenges of programming quantum computers. So, for example, Bernardo says, on one hand, we have the problem of physically realizing quantum computers, but then there comes the problem of programming them. Could you perhaps comment on the various proposals of quantum programming languages that have appeared over the years? Is it possible to how far are we from having a quantum Turing machine or something like that? So what is your perspective about this?
Yeah, well, I mean, you know, as a theoretical model, we have quantum Turing machines, right? I mean, Deutsch defined them in the 1980s, and then Bernstein and Vazirani, you know, studied quantum complexity theory using quantum Turing machines back in 1993. Now, you know, the way that we normally think about quantum algorithms nowadays is not in terms of quantum Turing machines, but in terms of a different model called quantum circuits, okay, where we can just think, you know, you've got a collection of qubits, and now here are the operations that you do on the qubits, you know, which might act on one qubit at a time, or maybe on 2 or 3 qubits at a time. Okay, and then what about all of the, you know, conditionals, the for loops, while loops, control flow, memory? Well, all of that stuff, it turns out, can be handled by a classical computer, which is controlling the qubits. Okay, so you should think of, you know, and this is sort of both the theoretically most convenient way to define quantum computation. And it's also the way that, you know, it's also what the quantum computers actually look like in practice if you go into the lab. A classical computer is used for everything that you can use a classical computer for. And the qubits are used only for what they have to be used for. Okay, so sometimes people make a big deal about, you know, classical quantum hybrid methods. Okay, but the truth is every quantum computer is a hybrid of classical and quantum, right? You use a classical computer to, you know, do all of the interface stuff, basically all of the mundane stuff, right? All of the, you know, the user interface, the the abstractions, the data structures, right? And then the qubits are precious. You should think of them as a special purpose accelerator, right? That the classical computer has available to it to use for that specific part of the computation where qubits are actually going to help you, actually going to give you an advantage. And so from this point of view, programming a quantum computer could look a lot like programming a classical computer, but just with this additional, thing that you have to control with a microcontroller. Let's say, these, qubits that you then do operations on and then make measurements on to get results. Having said that, for the past 20 plus years, there has been a field of quantum programming languages that tries to, design, ways that you can write your entire program in a sort of quantum aware way. And there are, by now, there are a whole bunch of these quantum programming languages that already exist. They have names like, QuizKit, Q#, Quasm, they all have a Q in them somewhere. But you can actually download these things and play with them right now. Of course, you'll be running them in simulation on a classical computer, and it will be slow. But you can do it. Okay, and now I don't have a strong opinion about like which quantum programming language might be the best one. I feel like this is the kind of question that we might well not know the answer to, until we have a whole installed base of quantum computers and we have a whole community of people who are programming them, and then they will vote with their feet and and decide which quantum programming language or which tools for programming quantum computers they actually find the most useful. Right now we have no shortage of proposals. The sticking point is the actual hardware to run the quantum programs on.
Okay, so Scott, I mean, we are all really excited this discussion, but I guess we have to terminate at some point the talk.
Yeah.
But let me just ask you some final questions. I think it's interesting because
sure.
it points to a different direction. So one asks whether quantum computing, you think, how would it compare in terms of energy efficiency with traditional digital computing? So she further adds, how would quantum computing help fighting climate change somehow?
Yeah. Okay. Well, so let's start with energy efficiency. So, I mean, if you look at the quantum computers that exist right now, right, they have a big dilution refrigerator, right? That's cool. That has to cool a chip down to like 10 millikelvin or something, right? That uses a lot of power, right? I mean, just, almost all of what you see is just the cooling system, right? But cooling takes a lot of power, right? So it's not, it's not especially energy efficient, okay? But having said that, it all depends on what you're trying to do with the computer, right? So people, have pointed out the irony that the quantum, the supercomputer like Summit that you could use to simulate the Google Sycamore chip is actually using much more energy than Sycamore is using, to do the same task, right? So even though you've got this big dilution refrigerator, it's still using a lot less energy than a supercomputer that fills 2 basketball courts, right? And and in general, right, if you use the quantum computer to do something like factoring a 4,000 digit number, right, that might take, like with the kind of designs that people envision today, that might take like enough energy to power a building, or at least to power like a floor or something, right? It might take a quite significant amount of energy. On the other hand, to solve that same problem with a classical computer, for all we know today, would take more energy than exists in the entire observable universe. Okay, so so that's quite a speed up in energy efficiency, right? But so as I said, it all depends on what you want to use the computer for. Now, in terms of climate change, there have been speculations that, one of the main purposes of a quantum computer would be to give us a new window into chemistry, right? To sort of revolutionize our ability to design things and simulate things at the nanoscale. And you could use that for all kinds of things. One example of what you could use it for would be to design new carbon capture mechanisms, right? Or to design, new solar cells, that would be more efficient, right? But there are a bunch of steps between here and there, right? You could also imagine using a quantum computer to, simulate, the effects of cancer drugs, right? Or how some protein binds, right? So there are lots and lots of applications that you could imagine to some of the great societal challenges. But the hard part was, well, first of all, we have to build the fault tolerant devices, which could take decades. And then you have to be not only the best classical computers that exist today, running the best algorithms that exist today, but the best classical solutions that anyone will have by then, right? So it's a moving target, and so it's not obvious if quantum computers are going to help with these great challenges. But I'm hopeful that and a key point is that we only have to see one or two benefits. Like if you had one or two victories, in designing a new chemical reaction that could help with climate change, then that could just by itself economically justify the entire investment that there's been, in this entire field.
Okay, so I think we could go on and on for hours, but at some point we have to close the session. So I have lots of questions still hanging here on the chat. So I promise just to put them on a file and send them back to Scott, if only for him to inspire some new explanations some other time, some other point. So I think we are really thankful for your talk, which was really inspiring. And let's just all together do a kind of a virtual applause here. I don't know how this should work, because all of us have the mic closed, but using this end, so I can almost take a picture of that. So thank you very much, and see you soon, some other time, some other place.
Well, thank you for having me. I'm sorry that I was not able to get to all of the questions. I do. You can look at my blog. People are asking me stuff all the time.